actually happening at equilibrium and figure out which of these other particle systems is at equilibrium currently. And so in this case, the equation is 2 green plus 1 orange gives you 2 blue. And so what I'm actually going to do is write out what this would be as an equilibrium constant. So in this case, Kc would equal, remember it's products times their coefficient power to their coefficients powers. So I'm just going to write this as blue squared over, in this case we have green squared times orange. So looking at that, and it says that this picture here is already equilibrium. And so what we can find is that if we look at the ratio of these things to each other, we know that they're equilibrium, so we can actually figure out a Kc value. And to do that, we're just gonna fill it into this equation. So we have blue squared, which in this case is gonna be 4 squared, divided by the number of greens squared, which is 2 squared, times the number of oranges squared, which is 1. So this actually gives us 16 over 4, or I'll write that over here, that K equals 4. Once again, if there's any questions, just put it in the chat and I'll read those as I go and I can slow down, but assuming you all follow at that point. So basically all we did was use this picture to determine a K value. The next thing we're gonna do is actually determine what the Q value is, I guess, for A, B, and C here in the images and see if they're at that equilibrium constant ratio. And so to do that, first we're gonna look at A. So for A, remember it's just blue squared over green squared times orange. So for A, we have, in this case, 6 squared over 3 squared times 1, which means we have 36 over 9, which equals 4. So A here is actually at equilibrium. We'll check the other two now to see if they're at equilibrium as well. So looking at B, there are 1, 2, 3, 4, 5, 6, 7, 8 blues. So to do that, remember it's going to be Q equals 8 squared over 1, 2, 3, 4, 4 squared times 1, 2 times 2. So that ends up giving us 64 divided by 32, which actually ends up equaling 2. So B here is not at equilibrium because the Q value determined is equal to 2 and not 4. Lastly, I'll do C. And so looking at C, it's going to be a pretty similar problem. So looking at this, we have 1, 2, 3, 4, 5, 6 blues. So remember Q equals, in this case, 6 squared divided by 3 squared for the greens times 2 for the oranges. And that gives us 36 over 18, which also equals 2. So this one isn't at equilibrium either. So I have a good feeling that there will be a question like this on the exam, just based off what he's talked about. So make sure you're comfortable doing these. And once again, if you have any questions, I can go over it again. But the trick is, don't just look at the ratio here. You'll actually have to figure out what that K value is originally, and then go through and figure out the Q values of each of the others. So if you're all good with me moving on, then I'll jump into number 3 here. And so for number 3, it basically wants you to determine if you decrease the volume, what's actually going to happen to the reaction. This goes back to the, can't think of the word off the top of my head. What is it? You know what I mean. Sorry. So looking at this, basically, as you add to the volume, it's going to move to the side that has more moles. If you decrease the volume, it'll move to the side with fewer moles. The trick for this problem is that it's actually not balanced to start with. and you only look at moles of gas for when it takes up space. And so looking at this, the first thing you have to look at is the equation balanced? And on this side, we have 2 carbons. This side, we don't. So right off the bat, we know that it's not going to be balanced. So what I'm going to do is actually just start balancing the equation. In this case, it's actually pretty easy to balance. All you'll need to do is add 2 in front of this CO and a 2 in front of this H2, and then everything should be balanced. So now there's 2 carbons on each side, 4 hydrogens, 2 oxygens, and so on. Looking at this from this point then, all you're going to have to do is figure out total moles of gas on each side of the reaction. So looking at the reactants, we have 1, 2, 3 moles of gas here. So we have 3 moles of gas. On the product side, now that we've balanced it, we actually have 4 moles of gas. So remember, if you decrease the volume, it's going to point it in the direction of which has fewer moles of gas. So in this case, that means the reaction will favor the reactants. So the reaction is going to go that way, and I'm just going to say produce more reactants. Okay. So moving on then to number 4, remember for any of these types of problems, you're looking at the number of oxygens that the acid has. The reason that you look at that is the more oxygens it has, the more the electrons are going to be drawn away from that proton, and therefore making it easier to lose that proton. And so basically for this problem, I'm just going to write, so more oxygens equals more acidic. And this problem might be kind of easy because HNO3 is one of your strong acids. But looking at that then, so this is going to be the strongest. And then HNO here is actually going to be your weakest, with HNO2 being in the middle. That's just something I wanted to quick review because, once again, I think there's a pretty good chance you see something like that on the exam that you're going to be taking tomorrow. So just remember those trends. Moving on to number 5 then. This is when we're going to start getting to some of the acid and base calculations. And so for this one, it says that you're given a certain mass of a monoprotic acid, and it's dissolved in enough water to produce a 25 milliliter solution. And so it basically tells you that the solution has a pH of 4.93 and wants you to determine the Ka. So you should have seen something like this on your homework assignment, but looking at what you actually do for this is you will basically just figure out what information you know and then determine how you can actually find that Ka. And so a few things I'm going to do to start with. It gave us a mass of the acid. We obviously don't really know how to work with the mass of an acid. We need to convert that to moles to be able to determine concentrations or anything to do with equilibrium. So to start with, what I'm going to do is actually just convert 0.272 grams into moles using this molar mass here. And so I'll do that up here. We have 0.272 grams. And then we have that 1 mole is 189 grams, which ends up giving us a total number of moles of 0.00144 moles. And then the next thing that we have to do is, once again, for any of these problems, we've been converting to molarity, not just number of moles. And so what I'm actually going to do is divide this number of moles by the volume in liters to get to molarity. So I'm just going to do this divided by 25 milliliters is the same thing as 0.025 liters, which ends up giving a molarity of our acid of 0.05757 molar. So looking at this then, we now have the initial concentration of our acid. We are also given the pH, and that's all the information we have to start with. So what you need to think about here then is what the Ka actually tells you. And remember, for any of these problems, Ka equals the concentration of H3O plus times the concentration of A minus over the equilibrium concentration of HA. And remember, HA is just the generic form of any acid. A minus is the generic form of any conjugate base of that weak acid. So looking at this then, I'm actually going to set up the ICE table then as well for how you would solve this problem. And so looking at how the ICE table would work, just generically, once again, you have HA plus H2O gives you A minus plus H3O plus. H2O, remember, you don't count because it's a liquid. I forgot to put the states of matter, but the rest of these three are all aqueous. So looking at HA then, we said we started off with 0.05757 molar. In any acid-base reaction like this that doesn't specify, you can assume that the A minus and H3O plus concentrations are 0. So I'm just going to plug in 0 for both of those. Then, as with anything, when you have 0 on one side for an ICE table, this is going to be minus X, this is going to be plus X, and this is going to be plus X. So you end up getting 0.05757 minus X over here, X and X. And so obviously right now we need more information to be able to solve because we'd have two unknown variables, X here and the Ka that we're solving for. But what you can do then to figure out what the concentration or what the value of X is, I guess, is you can actually use the pH then, because remember, pH equals the negative log of the concentration of H3O plus. And by default, the other way you can do that is that concentration of H3O plus equals 10 to the negative pH. And so looking at that then, since the pH is 4.93, the concentration of H3O plus then is going to equal, in this case, 10 to the negative 4.93. Obviously, this isn't in actual scientific notation yet because you can't have a decimal in the exponent. However, since we're just going to be plugging this in our calculator, we can use this. And so since the concentration of H3O plus at equilibrium equals this, and at the same time, it also equals X, because X is the concentration at equilibrium, we know now that this equals X. So to solve for Ka then, we can actually just plug in these equilibrium concentrations. So A minus times H3O plus over the equilibrium concentration here, which is 0.05757 minus 10 to the negative 4.93, and just plug that in our calculators to solve for Ka. So I'll move that over here while I have a little room. But we have then that Ka equals 10 to the negative 4.93. And I'm just going to square that because we end up having x squared over here since it's two x's times each other, divided by 0.05757 minus 10 to the negative 4.93. And that gives us a value that Ka equals 2.40 times 10 to the minus 9th. Okay, I don't see any chats, so I'm going to assume there are no questions on that so far. Once again, feel free to stop me at any time, but I'm just going to keep moving on. Looking at number 6 then. So I did end up they're not going to have you determine the percent ionization of a base, and so I wasn't reading this problem too closely when I wrote this, so we're going to just cross out this part, by the way. So we can maybe do percent ionization a little later, but we won't do that for this problem because it's using a base. But for this one, it wants you to determine the pH of a solution containing a certain concentration of sodium fluoride. And it gives us the Ka for hydrofluoric acid. And so looking at this, the trick for this problem, I guess, that you should hopefully be somewhat familiar with by now is that you'll basically have to find the Kb value for the conjugate base of hydrofluoric acid. And to do that, all you're going to do, remember, is do that. So start with Kw equals Ka times Kb. Or we then have that Kb so Kb equals Kw over Ka. Looking at that then, basically what you can solve, you know that Kw equals 10 to the negative 14th. So we're going to have 1.0 times 10 to the minus 14th divided by 3.5 times 10 to the minus 4th. We end up getting then that our Kb equals, let's see, 2.87 times 10 to the minus 11th. Okay, that kind of worked. Not great with writing with a stylus, I apologize. And so then looking at what we have then, we have a Kb value. All we have to do then is determine, first of all, what this reaction would look like in an ice table. And so remember the generic equation for a base reacting is we're going to basically have A minus. I'm going to shift this over here a little bit. So we have A minus plus H2O gives you HA plus OH minus. And so H2O, as usual, is going to have a concentration of 0. Looking at this, we can assume that these concentrations are also 0 to start with because it didn't tell us otherwise. Looking at the concentration of A minus then, that's just going to be the concentration of sodium fluoride here, which is 0.066 molar. So I'm going to zoom in on this a little bit. So we have 0.066 molar. We're going to then subtract x from this side because there's nothing over here. So you have 0.066 minus x. This will be plus x. This will be plus x. And so both of these just equal x. Looking then at what Kb equals, it's just going to be products over reactants to their coefficient powers. Or in this case, we then have that Kb equals x squared over 0.066 minus x. Looking at this then, we know what the Kb value is. So Kb equals 2.87 times 10 to the minus 11. And so what you're going to have to do then is plug this into your calculator and solve it. So I would show you how to plug this into my calculator. It is a little difficult to show that, just how I'm doing this. So if you are having calculator problems, please just stay after class a little bit and I'll keep going and answering questions and I can kind of show you a little more easily then. But just trust me that I put this in my calculator and that we end up getting that x equals 1.37 times 10 to the minus 6. Then what we have to look at is we have to be careful here. It wants to find the pH. What the x value actually gave us for this problem is both the OH minus concentration and HA concentration. It did not give us the H3O plus concentration. But what we can do still is we can basically, if we take the negative log of this, we're going to end up getting the POH. So if we take the negative log, we get that the POH equals 5.86. And so if you find the pH then, pH will just equal 14 minus that. And that equals 8 point, basically 14 with 2 sig figs. So I know Dr. Couts kind of mentioned it in his lecture today, but so since this test is through Canvas, it's not going to really grade you off sig figs. So I would actually, if I were to tell you, just put in more digits than fewer to be safe, because then you're still going to be closer to the actual answer. I would not worry about sig figs too much, just because, as I said, if you type it in, the computer doesn't know better. But if you put in an extra decimal or so, if it doesn't ask for a specific number, you might as well, and it'll probably be more likely to get it right than if you round it off too early. Looking at number 7 then, just gonna move on, is basically determining the pOH of a solution containing basically a weak acid, acetyl salicylic acid, and perchloric acid. And so the key for this is actually not really one of our buffer solutions yet. What this is telling you is you have a weak acid here with a strong acid. And so if you think about what's happening, I guess this is a type of buffer, but what you have is HClO4 is going to go into solution. And because it's a strong acid, for every 1 mole of perchloric acid, you're going to have 1 mole of H3O plus. And so in this case, we have 0.012 molar H3O plus. And this is actually going to be that initial H3O plus concentration in this case. And so all I'm going to do to calculate the pOH for this problem is do another ice table where we have HA plus H2O gives you H3O plus A minus. But for this problem, what I'm going to do is actually put in for HA, or sorry, yeah, I did this backwards. So this should be A minus, and this should be, oh no, I was doing it right. Okay. Sorry, I panicked. Okay, so this is HA, and this is going to be A minus. So as always for an ice table, water is going to be constant. Looking at this, we're going to have 0.024 minus X. Oops. So the original is that. H3O plus, we said the original is now going to be 0.012. And then this, we still have 0. When you need to figure out which direction you're going, looking at this, when you have 0 as any of the reactants, you know that when you multiply these two together, it's going to be 0. So in this case, Q is going to be less than K, and the reaction is going to go this way. So we're going to do minus X here, plus X, and plus X. So we end up getting 0.024 minus X, 0.012 plus X, and X. And then what we're going to do is make this equal to the Ka in that reaction quotient type deal. So what we're going to do then is we have X times 0.012 plus X divided by 0.024 minus X is going to equal the Ka here. So this is going to equal 3.3 times 10 to the minus 4th. Once again, I'm just going to plug this into my calculator, and you end up getting that X equals 6.12 times 10 to the minus 4th. Looking at what this actually tells us then, X does give us the A minus concentration. However, it doesn't actually give us the H3O plus concentration. That is equal to 0.012 plus X. So to find the H3O plus concentration, what I'm going to do is actually do I'll write that here. So concentration of H3O plus equals 0.012 plus 6.12 times 10 to the minus fourth. This ends up giving us that the concentration of H3O plus equals, where is it? 0.012612. To find the pH then, I'm going to take the negative log of that. So the pH is going to equal 1.899. The pOH then will equal 14 minus that, or pOH equals 12.10. And so that will be our answer to this problem. Are there any questions on that? Okay. So moving on, we'll jump to number 8 here. So this is one of the first ones that we're going to work with an actual buffer system. And so before I move on too far into this, I am going to actually kind of talk about how buffers work. I don't know if any of you saw the review worksheet I posted, or I think it's called Exam 3, like Stuff to Know. And so obviously now that it's open note, you don't actually have to memorize all of these things. However, it kind of gives you a tip as some of the equations built in here. This periodic table just tells you what the strong acid and base anions and cations are. But moving down, this is where I'm going to actually start using the Henderson-Hasselbalch equation. And it looks like, I apologize, but in the PDF form, apparently it does not load the equations that I had in Word. So I will just write those in really quickly. So for pH here, this log term is just going to end up being moles of base over moles of acid. So once again, this should be what's in those parentheses. Moving on down here for the pOH form of this, it's going to be moles of acid over moles of base. And so those are the two generic forms of the Henderson-Hasselbalch equation. I'm not going to go through all of these. Once again, if you download the Word document on Canvas, it will give you these actual details. These all have something to do with if you add a strong base or strong acid to a buffer system. Basically, I'm going to use one of these forms for the equation I was solving. But for now, once again, trust me, the Word document actually has something in here, which is pretty helpful. So for example, for this one, the pOH, if you're adding a strong acid, what you can do is that it's going to be log here of moles of acid plus moles of strong acid added over moles of base minus the moles of strong acid added. And once again, for any of these equations, this is the same stuff that Dr. Kautz did in his lecture today, if you've watched that. However, what this basically does is what he did in class was, I'll just do that right here. So he said, let's say that the Ka equals the concentration of H3O plus times A minus over HA. All this equation does is, remember what pH is it's going to be the negative log of the concentration of H3O plus. So if you actually take the negative log of everything here, you end up getting that you have negative log of Ka is actually equal to pKa, which equals the negative log of H3O plus, or pH, then minus the log of A minus over HA. And then all I did from this step to here is basically you bring this log to the other side and you get the Henderson-Hasselbalch equation. And so I just like to use this form because usually you're working with pH or things like that. The important thing for this is just remember that pKa equals the negative log of the Ka, and that ends up letting you solve. And I think this makes these equations a lot easier than if you actually had to plug them into this form. I just think this gets a little confusing. So once again, I like to use this form. You can use either one. They'll give you the same answer. They're actually the same thing, but you'll see the Henderson-Hasselbalch equation a lot more often. I know Dr. Couts does not like to teach that. So I'm just going to use that for this problem though. So moving on then, basically, if you use that formula, I said for this one, you're basically having, it gave you a Kb value and you're adding a strong acid. And so all I'm actually going to do is plug this into that version of the equation where you end up using the POH and adding a strong acid. So for this case, the equation says POH equals PKB plus log of moles of acid plus moles of HCl divided by moles of base minus moles of HCl. So we know this is what we're going to have to plug things into. Basically, first of all, you're going to have to do some converting. And what that's going to be is converting these things into moles instead of molarity. You can use molarity as well, but I think for these problems, because you end up having volumes cancel out, I'm just going to use moles over moles. And to do that, it's going to be basically, we have 500 milliliters is 0.500 liters times 0.100 moles per liter. And that ends up equaling 0.050 moles. And I'm not going to label this because if you notice, this is actually equal to moles of NH4Cl as well as NH3 because they both are 0.1 molar concentrations in the same solution. So I'll just label that, I guess, as NH3 and NH4Cl. The second thing then is I'm going to find out the number of moles of strong acid that I'm adding. And in this case, we're adding 15 milliliters of 1 molar HCl. So to do that, we have 0.015 liters times 1 molar, which ends up equaling 0.015 moles of HCl. So we have these terms then. So we know moles of acid, moles of base, and moles of HCl. We do not have the pKb yet, but we do have the Kb. Remember, the Kb is just a negative log of the Kb. So I'm going to write that here as well. So we then have that pKb equals the negative log of, in this case, 1.8 times 10 to the negative fifth. And after that, we have all the terms we need for this equation. So I'm just going to plug everything in. We will solve for the pH with this equation, but it's a pretty easy conversion to get to pH once we're done. So all I'm going to do then is when I plug these things in, we end up getting that POH equals the negative log of 1.8 times 10 to the negative fifth plus the log of, in this case, we have 0.050 moles plus 0.015 moles HCl. Over 0.050 moles minus 0.015 moles of HCl. And then when you plug this into your calculator, you should get that the POH then is going to equal 5.014. Looking at sig figs, once again, they shouldn't be too important for this exam, but the KB only had 2 sig figs, so this is going to be the last significant figure. However, we also need to convert this to pH first. I'm getting ahead of myself. So the pH then is going to basically equal 8.99. And once again, to get to the pH, all I did was subtract this value from 14, and then we're good. So are there any questions on that? Okay, so for this form, or for this equation here, or not equation, this problem, number 9, basically it wants you to figure out which choice is the best to make a buffer of a pH of 3.5. And so all you want to look at for a problem like this is you're actually going to figure out what the pKa is, and whichever pKa is closest to the desired pH is what you want your buffer to actually be chosen. So looking at this, the first thing I'm going to do is actually cross off hydrochloric acid here. And the reason for that is HCl is going to be a strong acid, so we know its pKa is going to be really high, or really low, I mean. So this one is not a good buffer choice at all. You can't really have a strong acid as part of a buffer. But looking at the other options, they all have some potential. So what I'm going to do is actually take the negative log of all of these values. And so if you take the negative log of 1.8 times 10 to the negative 5th, you end up getting 4.74. If you take the negative log of this one, you get negative log of 1.8 times 10 to the minus 4th. This one gives you 3.744. This one, if you take the negative log of 3 times 10 to the minus 8th, you end up getting 7.52. I'm not going to write this out again, but I'm just going to write this value of 7.52. And then for the last one, if you take the negative log of that, you end up getting 3.167. So in all honesty, this was an old exam question actually, so I'm not sure why they made them this close. But looking at this, both formic acid here and hydrofluoric acid would probably be okay for making a buffer for this. But once again, you just want to use whichever one has the closest pKa to that pH. And in this case, 3.744 is a little closer. So this is going to be the actual answer that you'd probably want to put for the exam. Okay, I'm just going to move on. This one, I just wanted to throw in there to emphasize in case you're a little confused. I already did this earlier, but this one should be a pretty simple problem. It's just literally figuring out the Kb of its conjugate base. It does start with a pKa, not a pKb though. So looking at this, or not pKb, I mean, it doesn't start with the Ka, it starts with the pKa. And so remember, if you ever want to get out of like the p function, so this basically equals a negative log of the Ka. To figure out what the actual Ka equals, in this case, Ka will equal 10 to the negative 4.76. What I'm going to do with that then is literally just convert this to Kb. To do that, all I'm going to do is do 1 times 10 to the minus 14th divided by 10 to the negative 4.76, which is going to end up equaling 5.75 times 10 to the minus 10. And remember, this is because we have that Kb equals Kw over Ka, which equals this. And once again, if you're just putting it in your calculator, you can leave it in this decimal form. You don't actually have to convert it out, but you can. It's up to you. Salts, and you're going to have to determine whether or not they, like the combination of these two, ends up equaling or just basically equating to form a buffer. And so to clarify what a buffer is, it's basically a combination of an acid and its conjugate base in a solution, and that's all you basically have to look for. And so looking at the first one here, you have NH3 and NH4 plus. This turns into NH4 plus in solution, so I'm just gonna write this as NH4 plus. Looking at this, do you have a weak acid and its conjugate base? Yes. And so when you ever you have a weak acid and its conjugate base, you know that it's going to be a buffer. So this one will be a good buffer here. B is actually probably one of the more tricky ones. And the reason is what it looks like you have right now is this is what we already said, a weak acid, but you also have a strong base. And so on first glance, you would say this can't actually be a buffer. However, what's actually going to happen whenever you have a strong base with a weak acid is it's going to completely turn some of this strong acid into its basic form. Because if you look at what's happening, if you have NH4 plus, this turns into OH minus, you end up getting NH3 plus H2O. And so it's going to do that until you're out of KOH. And so as long as you have fewer moles of KOH than you do of NH4Cl, you're actually going to have a ratio then in the solution of NH4 plus, I forgot that, and NH3. And so because you have both of those things in solution, B here is actually also going to be a good buffer. And so I do mention that special case, I guess, on that review worksheet or packet thing I made as well. So just keep an eye on that. You can use that during the exam if you'd like to, but just make sure you keep that in mind that as far as buffers go, those things are possible. Looking at C then, I guess I should clarify before we do this one. Remember, it's going to be a weak acid in its conjugate base. Looking at this, you have an acid in its conjugate base. However, hydrobromic acid is not going to actually be one of your weak acids. This is one of your strong acids, which you should know. So when it's one of your strong acids, what that means is that it actually can't be part of a buffer situation because your Br minus here isn't actually going to be a base. This is one of your neutral anions. So I'm just gonna write that here. Because it's a neutral anion, this won't form a buffer system. So this one actually isn't a buffer, even though it kind of looks like it on first glance. The last one then, you have a weak base and a weak acid. However, they're not aren't conjugate acid and bases of each other. They're just two separate acids and bases. So these two will not be a buffer system as well. So once again, I'll be able to answer questions on that when I'm done. I'm just going to do this last problem here, and then I'll kind of open it up for any questions and stop recording. And then you guys will be free to go. So looking at this last one then, this is just kind of another question regarding buffers. And so for this equation, I'm basically going to use the form of the Henderson-Hasselbalch equation where we have pKa equals pH plus log of the base over log of the acid. Oop, I wrote that wrong, sorry. So it's actually going to be pH equals pKa plus log of the base over log of the acid. So looking at this then, I think I actually wrote this wrong on the answer key too, so just keep an eye out for that. I apologize. I'll change that in a second. But looking at this then, so we have our desired pH is going to be 10. We have the pKa is 10.732. And we want to know how many grams of this form must be added to this to make a solution with that pH. So looking at that, this is going to be the base, and this is going to be the acid, because this one has one fewer proton than this one does. So looking at it then, we end up having that we basically need to convert to moles of acid, moles of base. So looking at this, we have a certain volume of this with this molarity. So I'm going to find out how many moles that is. So to do that, we're going to do 0.250 liters times 0.20 molar, which ends up equaling 0.05 moles of the acid. So we now have the acid over here. Didn't mean to put log there. So log of base over acid. We have acid. We just need to solve for base at this point. So all I'm going to do then, I guess I don't know why I wrote that here. 1 second. So we end up getting this plus log of moles of base over 0.05 moles of acid. To do that then, just solving, you get minus 0.732 equals log of moles base over 0.05 moles. So I'm actually going to do then is take 10 to the minus 7.732, and you end up getting 0.185 equals moles of base over moles of acid. Then lastly, all you're going to have to do, I should write this as 0.05 moles, sorry. All you're going to have to do is multiply both sides, and that gives us 0.00927 moles of base. All you have to do then is, this problem actually asked for the mass, and I did not write the molar mass. However, the molar mass for this is going to be 45. I'll write that up here. 45.09 grams per mole. So all I'm going to do then is convert this number of moles into grams. So we have times 45.09 grams over 1 mole. And you end up getting that this equals 0.418 grams. And there you go. So thank you guys for watching. I'll basically open it up. If you wanna, you can send it in the chat or just unmute your microphone and ask any questions. I'd be happy to go over anything. I'm kind of like transitioning into my office hours now. So I'll still be on for another 40 minutes or so. If any of you want more help with anything, I'll be here. But if not, thanks for tuning in. I will also post this lecture on YouTube at a link that's posted in Canvas if you'd like to rewatch or follow along there at all.